All right, so let's get back into it. We're going to do something exciting now. So you've seen QFT so far, and I think you also have good enough intuition now to see exactly how we would actually do this in a quantum circuit. All right, so I'm going to start a clean page and say, so let's go through the process of building the quantum circuit that applies the quantum Fourier transform. So what does it take to build that quantum circuit? Well, we need to go through two things. The first thing is I need to show you what QFT is rigorously. So far, we've been talking about pictures of how to look at QFT. And secondly, I'll show you from this rigorous implementation, the reason we're going through it is not just for the sake of rigor, but also because that explanation shows you exactly the circuit components that you need to implement QFT. So show circuit to implement QFT expression that comes from 1. And by 1, I mean this. Okay, so let's get started. So let's imagine first of all that we're dealing with n qubits. So I'm going to write that down by saying we have n qubits. And I strongly recommend, as I'm doing this, that you follow the discussion that I'm going to make here, but the lecture notes will be available afterwards. So it's very important for you to be looking at the details of what I'm writing instead of trying to go through on your own. There's plenty of time to go through it on your own, but let's go through this very quickly. So let's say you have n qubits. And what does that mean? So for example, in the 1 qubit case, you had the states 0 and 1 in your computational basis. So there were 2 basis states. For 2 qubits, you had 0, 0, 0, 1, 1, 0, oops, and 1, 1. So that's 4 basis states. And more generally, for n qubits, you have 2 to the power of n basis states. So I'm going to define a new variable. I'll call it big N, and I'll say big N is 2 to the power of small n, just so that we don't have to keep writing 2 to the power of n over and over again. Okay, so we'll write this once and use it repeatedly. I told you earlier that I was going to use the notation of a tilde when I do a quantum Fourier transform. So I'll define x tilde to be the quantum Fourier transform of x. Simple enough. So x tilde is going to be in the Fourier basis, as we talked before. And x here itself is going to be in the computational basis. All right, what does this do? For those of you who are maybe electrical engineers, have done some sort of signal processing, that sort of thing, the quantum Fourier transform is exactly the inverse discrete Fourier transform that you've seen classically. So the expression for it looks something like this. So you have a normalization coefficient here, 1 over square root of n. And then you have y going from 0 to n minus 1. Because we're starting from 0, you have that minus 1. E to the 2 pi I, complex number, x, y over n, and the state y. That's it. That is the definition of the quantum Fourier transform. It's very simple to write down, but let me show you exactly why this works. So for example, you might remember we talked about the 1 qubit quantum Fourier transform being the Hadamard gate, but let me show you something very cool. So let's do the 1 qubit case. So in 1 qubit case, n is 2 to the power of 1, which is 2. So let's write down exactly this expression. QFT of x is 1 over 2 square root sum from y equals 0 to 2 minus 1 e to the 2 pi I x times y over 2 with a y here. Okay, sounds good. It looks like we have a sum going from 0 to 2 minus 1, which is 1. So let's write down that sum explicitly. And remember, there's this 1 over square root of 2 here. So that is exactly 1 over square root of 2 of e to the 2 pi I. So for example, when y is 0, the whole exponent is 0. So e to the 2 pi I x times 0 over 2 with a 0 plus, when y is 1, it's e to the 2 pi I x times 1 over 2 with a 1. That's it. QFT of x is exactly that. So this one goes away, so that's just 1. And here I can cancel out the 2's and write this down to be 1 over square root of 2 of just 0 plus e to the I pi times x 1. Okay, let's see why this works. So you already know the answer from what we discussed earlier, but we said QFT of 0 is plus, right? But can we prove that? So let's do the case for QFT of 0. QFT of 0, according to the expression we've written out, is 1 over square root of 2 of 0 plus e to the I pi times 0 is multiplied up here, and that just removes this, removes that to be equal to 1. So this is just 1 over square root of 2 of 0 plus 1. That's not surprising. That's exactly what we call the plus state in our first lecture. What does QFT of 1 look like? Remember, this is the minus state. What does QFT of 1 look like in the way that we've written it up here? So that is just 1 over square root of 2 of 0 plus e to the I pi. This time x is 1 times 1. And if you remember, e to the I pi is equal to minus 1. So this is 1 over square root 2 of 0 minus 1. And that's exactly the definition of what we call the minus state in our first lecture. So you see the notation that you've seen already and this way of writing down the quantum Fourier transform are equivalent. So this is only an example for 1 qubit, but more generally, this works for any number of qubits. So from now on, as we write through these things, I want to show you something to be careful about. As you're reading the textbooks in general or anywhere on the internet, there's kind of a small abuse of notation that people do here that I want to bring your attention to so that you're not confused when you see this somewhere else. So when we have, let me change the color here. A note on notation for multiple qubits. I will say, for example, when we're talking about, let's say, 3 qubits, let's say the following. The definition of the quantum Fourier transform, again, for the case of 3 qubits, where, again, we have 3 qubits, which means 2 to the power of 3 is 8. So you have this 8 in front, and you have y going from 0 to 7 of e to the 2 pi I. And you have x and y divided by 2 to the power of 3 of y. When you see something like this, notice the sum. The sum is going from 0 to 7. So the numbers in here are going from 0 to 7. But what exactly does that mean, going from 0 to 7? So let's think about exactly what that means. So if we say y is 4, first of all, this may not seem like a sensible thing to write, right? Because we've said y looks like things like zeros and ones. 0, 1, 0, 0, 1, 1, and so on. You're used to seeing states written down as zeros and ones. What does it mean to have a state like this? This is the abuse of notation that I'm trying to give you a warning. Every time you see something like this, what it really means is the binary representation for that number. So 4, for example, is 1, 0, 0. So that's what that expression means. Because writing all these 0 and 1s can be a bit laborious, you see people writing down either the 1, 0, 0 type notation or just writing down 4. The important thing to be careful about when you're doing these kinds of things is that here the sum is going from 0 to 7. So keep that in mind. If we were dealing with the binary representation instead, what you'd need to do is write out y as a series of numbers. So y1, y2, y3, up to yn, if it's an n qubit case, and make the sum not go from 0 to 7, because you can't anymore. These are bits. They're all zeros and ones. But make the sum go from, so y0 to 7 becomes y1 goes from 0 to 1, y2 goes from 0 to 1, y3 goes from 0 to 1, and so on until the last number, yn, goes from 0 to 1. So this is why you see people changing between the two notations. It's quite laborious to write down this very long way, so you see people summarizing it in this way. I just wanted to warn you about this so that it's very clear when you're going and looking at other references what exactly people are trying to write down. I found this personally a little confusing while I was learning. All right, so let's go through this. How do we use the expression that we've seen so far? At least right now, this expression doesn't tell me much about how to build a quantum circuit to do this work. I really can't tell what the quantum circuit looks like for the quantum Fourier transform by looking at that expression. So we need to do a bit of manipulation here. So this is the part where I encourage you to pay attention here, but really what matters is the point that we're getting to. So if you're maybe missing a couple of steps, I would encourage you to rewatch this. It's a very short explanation, but it's something that's worth seeing the first time so that you're going to know exactly what is being done in these manipulations when you see them in other algorithms. Okay, so I'll write down again what the definition of a quantum Fourier transform. This time I'll use a different color, maybe a different kind of blue, so that you can separate this page as the derivation page. All right, so x tilde is 1 over square root of n, sum from y going to from 0 to n minus 1, e to the 2 pi I, x times y over n, and we have y here. All right, so I'm going to do something quick here. Let me remind you again, n is equal to 2 to the power of n. That's how we've defined it earlier. I'm going to do exactly what I showed you up here. Remember that y is not a number, is a number here that's going from 0 to n minus 1. I'm going to break it down into its binary. So I'm going to write down y is y1, y2, y3, going all the way to yn. And when I write down these square brackets, what I mean is that the decimal representation is simply 2 to the power of n minus 1 y1 plus 2 to the power of n minus 2 y2 plus going all the way down to 2 to the power of 0 yn. If you don't recall exactly what this is actually simply going back and forth between the decimal and binary representation of y. So for example, you might say if y is 3, that's in binary, so that's 1, 1. And that's, so these are 2 bits, right? That's 2 to the power of 1 times that 1 plus 2 to the power of 0 times the second one. So I'll put 0 here and say 1 here and 1 here. So this is the kind of notation that we're writing down. Okay, so let me make that a bit more explicit. Let's write y to be sum from k equals 1 up to n, yk, so now it's in binary form, 2 to the power of n minus k. That's exactly what you see here, written out in a more compact form. Then x tilde becomes 1 over square root of n, sum, so now notice how y is going from 0 to n minus 1 here. And we have e to the 2 pi I. And now is the part where we need to be a bit careful, right? So sum from k equals 1 up to n, yk, that's the power that we have here, 2 to the power of n minus k. There's an n at the bottom here. There's an n at the top here. So those two cancel out. So you're left simply with a yk here. And you have this expression y1, y2 going up to yn for y. So all of this is kind of a very compact way of writing down something that looks very complicated. If we actually expanded what this means, I think it would be much more clear. So I'm going to do that for you here. I'm going to say sum from y equals 0 to n minus 1. A sum in an exponential means a series of products. So I'm going to write down products going from k equals 1 up to n. And I'm going to write e to the 2 pi I x. So I forgot to write down the x here. X, and then the individual pieces of that product. So yk over 2 to the power of k. So there's a 2 to the power of k missing here as well. And we're going to have y1, y2, and so on, yn. Okay, so now that we've written all of this down, let's take that product and remember also y equals 0 to n minus 1 really is y1 is 0 to 1, y2 is 0 to 1, and so on up to yn is 0 to 1. So this expression, if you factor it out at the end of the day, really looks like the following. So the first bit, for example, if you isolate it, it looks like 0 plus e to the 2 pi I x over 2 to the power of 1, 1. The second one looks like 0 plus e to the 2 pi I x over 2 to the second power, 1. Tensor product. The third one looks like 0 plus e to the 2 pi I. I hope you're seeing a pattern here. 2 to the power of 3, 1. Going all the way to the last one, so I'll put a tensor product here, which is 0 plus e to the 2 pi I x over 2 to the power of n, 1. The reason you have these tensor products is because you have a product out here. And so what I did effectively here is move these sums, swap the order of the product and the sum, and bring in the terms separately, eventually getting you to this form. What's really important is that now, if you look at this expression, you have a way that you can then build a circuit out of this, right? These things look very similar to what you saw with the Hadamard gate. The only complexity is that they have these fractions on top of them, these 2 to the power of n. If there wasn't any 2 to the power of n, it's immediately obvious what to do with these circuits. So before we get too excited and start thinking about the circuit, let's just summarize what we did. All of this calculation can be boiled down to, we went from x, which really is just x1, x2, x3, and so on up to xn in binary. And really, that's just x1 tensor product with x2, tensor product with x3, and so on, all the way up to xn. We've taken that, applied a quantum Fourier transform, and we've ended up in a new form that looks like x tilde, which is 1 over square root of n, 0 plus e to the 2 pi I x over 2 to the power of 1, 0 plus e to the 2 pi I x over 2 to the power of 2, going all the way to 0 plus e to the 2 pi I x over 2 to the power of n 1. And I want to write it down this way because I'm trying to show you something really cool here. What we've done is take x1, transform it into this, x2, transform it into this, x3, transform it into something in the middle here, and xn, transform it into what you see here. Now you can see something very clearly, right? You can start imagining what these circuits might look like. The main difference between these kinds of the phases that's applied to each of these is that here and here and here you have different phases. So the question becomes, how exactly do you apply those phases? All right, so let's pause here very quickly and look at what happens for the case, for example, of 3 qubits. So let's say example, n equals 3 qubits. That means n, the big one, is 2 to the power of 3, which is 8. And what this also means is if we try to do, for example, x equals 5, again, this is the abuse of notation I was telling you about. Really, 5 is just 1, 0, 1. What does the QFT look like? QFT of x, which we've been calling x tilde, is 5 tilde in this case. And that's, you can immediately write it down, right? I'm going to do it for you. It's 1 over square root of 8. For the first one, I have 0 plus e to the 2 pi I. X is 5 over 2 of 1. Tensor product. For the second one, I have 0 plus e to the 2 pi I 5 over 2 to the power of 2, 1. And for the third one, I have 0 plus e to the 2 pi I 5 over 2 to the power of 3, which is 8, 1. That's it. That's really all it is. So I'm looking at the chat as I'm doing this, and I'm noticing some of you are asking, what does this X thing mean? It just means the states are separable for the individual qubits. So what I've done is simply say 0. So for example, if you've ever seen anyone say 0, 1, 0, really what they're saying is the state of the leftmost qubit is 0, the state of the middle qubit is 1, and the state of the rightmost qubit is 0. That's those two are exactly the same. So there's not much confusion here. So I hope you can see how powerful this is, right? I've just shown you not just an easy way to write things down, but also how simple it is to get the quantum Fourier transform. All right, so let's pause here because the next part is exciting. I'll show you how to take your learnings from what you've seen so far and build a quantum circuit out of this information. Before we do that, I'll take a quick pause here and ask Brian if there have been any questions.
Hey, there's been a few good ones. This one just got upvoted just recently. Beyond breaking cryptography based on the hardness of big prime factorization, could you make an example of the highlights of why Shor's algorithm could be useful other than that?
There are many other problems where looking for periodicity is important, not just for the cryptographic applications. In addition, the building block of Shor's algorithm, the quantum Fourier transform itself, is actually a component of several other algorithms, one of which you learned today, actually, the quantum phase estimation algorithm. So the pieces of Shor's algorithm apply in many different ways. Actually, in the original paper, there's another reason why Shor's algorithm is useful, and it's for computing discrete logs. So another different flavor of problem, but it's just to show you periodicity is the popular one that gets all the media and attention, but there are many other ways that it can be applied as well.
Great. And I also want to give a shout out to Shazvat, who's in the comments of the of all the questions, helping to answer questions via comment, so we don't have to do every single one of them on the screen. So thank you very much for doing that as well. And then one last question, Abe, for you. How can you have a guarantee over the complexity of finding a period if one exists? Isn't it a semi-decidable problem?
That's okay. So I think in the lecture notes I'll leave a very nice analysis of the complexity of Shor's algorithm. But that person is right. There are constraints that we need to place in order to write down the complexity like I have.
Perfect. Back to you.
Okay. So let's talk about the quantum circuit. It's very nice that there's a page break here because I can start a fresh new page and write down the quantum circuit that implements QFT. And in fact, something that will be useful for us is this form that I've written over here. So I'm going to copy it and hopefully do that right. Somehow I was able to do that right today. Okay. So we need this notation, right, in order to build out a quantum circuit from it. So this was the notation for x tilde. And let me just remove these additional details that are not important here. Okay, so each of these qubits went from, so I'll write down explicitly, each qubit went from xk. Again, I'll remind you, x used to be x1 tensor x2 tensor ... all the way up to xn. I'm writing it out with these spaces so that you see clearly what each one corresponds to. Each qubit went from xk to 0 plus e to the 2 pi I x over 2 to the power of k1. Okay, let's do a couple of things. So let's write down two observations from this. The first observation is that x tilde contains terms like, if you write out the product, so you have 0 here, you have 0 here, you have 0 here, and you have 0 here. Its terms look something like all zeros. And then all zeros except the last bit being 1, with a phase that looks like e to the 2 pi I x over 2 to the n. And even terms that look like when that 1 moves 1 bit over, it looks like 2 pi I x over 2 to the power of n minus 1, and so on. So that's your first hint that the number of the power here and the way the qubit is the one of the qubits is flipped to 1 is tied together. The second thing I want to point out is if you look at exactly what happens to these phases, that's the first observation. The second observation is that if you look at the 1, 1, 1 term, so here's 1, here's 1, here's 1, here's 1. If you multiply all of those together, what do you get? You get a phase that looks like this from this term, e to the 2 pi I x over 2 to the power of 1. You get another exponential from this part, which really looks like you're going. So if you're going to multiply two exponentials, I'm just going to keep adding them here in the exponent. 2 pi I x over 2 to the power of 2. 2 pi I x over 2 to the power of 3, going all the way to 2 pi I x over 2 to the power of n. And that's the phase in front of the 1, 1, 1, 1 state. If you add these together, what does that look like? That looks like e to the 2 pi I. Let's do that first. Let's factor that out. X over 2 to the power of 1, x over 2 to the power of 2, all the way to x over 2 to the power of n. So you learn two things from these forms, right? So so from this first expression, you can see that the way the phase is applied on each of these states is qubit dependent. So I'm going to just write down hints of form of circuit. The phase is qubit dependent. In other words, it seems that when a qubit is flipped from 0 to 1, the phase seems to change. So that's one hint that you can take from how all of this is done. The second thing is that look at this case, for example, where you had all ones. When you had all ones, you had to add all of these terms into the exponent. When you had all zeros, you had no terms to add in the exponent, so there was no phase. So it seems like you need, let me scroll up. You need to add up more components with more ones. Okay, that's that's another useful tip to think about. So I'm going to show you the two ingredients I'm going to use to build out this quantum circuit. Two ingredients. The only way I know how to create phases like 0 plus e to the 2 pi I something here 1, at least the very first way that I can think of is by using a Hadamard gate. So the first ingredient that I need is a Hadamard gate. A Hadamard gate applied onto a particular qubit with xk, so xk is either 0 or 1, is if it's 0, it's 0 plus 1 over square root of 2, right? You've seen this already. If it's 1, it's 0 minus 1 over square root of 2. In the literature, the way people refer to this is by doing the following. So you can compactly write, instead of having this branch going for 0 or for 1, you can compactly write this down as 0 plus e to the 2 pi I xk over 2, 1. That's it. What does this do? Well, this phase, e to the 2 pi I xk over 2, when xk equals 0, it is equal to just 1, because that exponent goes away. When xk is equal to 1, it goes to e to the pi I, which is exactly minus 1. And that's this branch. So the plus 1 branch is up here, and the minus 1 branch is the one at the bottom. So a Hadamard gate applied on a qubit with that generic state xk seems to do something that looks like this. So that's nice because it immediately gives us a way to apply at least these kinds of phases where 2 to the power of 1 is applied. Someone is saying square root of 2 is missing. Yes, you are 100% right. Thanks for keeping an eye on that normalization. So the Hadamard is able to get us phases that look like 2 to the power of 1 in that denominator. The second gate that I'll use is something that I'll call U rotation. And that U rotation gate needs a bit of information to know what to do. And that information that it needs is the value of K. When I apply it on a particular qubit state xj, I'd like it to do the following. I'd like it to apply e to the 2 pi I over 2 to the power of k xj on top of xj. So why do I need this? Well, this is the only way I can apply those denominators with higher powers of 2. So what does this look like? Well, if you look at this exponent, if xj is 0, e to the 2 pi I over 2 to the power of k xj is just 0. Nothing changes. If xj is 1, e to the 2 pi I xj over 2 to the k of xj is actually just e to the 2 pi I over 2 to the power of k of 1. UROT, here I'm calling it UROT, is to say unitary rotation. And I'm calling it a rotation because it's applying a phase here. So U rotation is exactly what that stands for. Okay, so notice the way to write down the matrix for this gate is the following. I don't know if you've noticed, I'm going to show you a very quick trick here that's very useful. This is a single qubit matrix. So first of all, we know it's 2 by 2. So there are 4 elements here. And I'm having to figure out what those 4 elements are. The elements here correspond to what this particular gate does to the state 0. And that's going to be giving you back exactly the state 0. So this is the state 0. The elements on the right are what it does to the state 1. And that's giving you 1 with a phase. So it's e to the 2 pi I over 2 to the power of k. That's the definition of that matrix. So we'll need that exact matrix in order to do our work. So the job of this matrix is to apply phase e to the 2 pi I over 2 to the k for state 1. All right. So now that you've seen how to do all of this, I would like to finally reveal to you, so if there were a theatric moment here, this would be the drum rolls where you'd see the circuit that makes up the quantum Fourier transform. Please be patient with me as I draw it out. So an n-qubit quantum Fourier transform.
Dave, I'm on the edge of my seat right now. I cannot wait.
Well, here we go. x1, x2, x3, all the way down to xn. This is what it means to do a quantum Fourier transform. So you would apply a Hadamard gate on this qubit, and then you would apply a controlled U rotation on this qubit. And remember, these U rotations require a number in order to define them. So I'm going to write down that number here. I'll say it's 1. And every time I write 1, it actually means 2 to the power of 1. So maybe let me be a bit clearer and write 2 to the power of 1, which is 2. Okay, so that's a controlled U rotation, which I'll write down like this. And then another U rotation, this time with power 3, coming from this bottom qubit. I want you to notice something here. This 2 came from this 2. This 3 came from this 3. Okay, so this line goes over. And another one is going to be applied here. From x4, we're just going to ignore that one. All the way up to the last one, which is UROT n, which is coming from this bottommost qubit. So that's all the gates that we need to apply just for x1. And this series of gates, I promise you, but I'll show you also explicitly, gives you exactly the terms that you get here. So you can already intuitively see this, right? I wrote down this expression for you, x over 2 to the power of n. You can see all of these rotations are applying different phases onto that first qubit. And remember, again, when I write down a number next to these UROTs, it means I'm applying a denominator here of 2 to the power of that number. So that's what you do to the first qubit. Then we need to deal with what happens to the second qubit. So we apply a Hadamard here and start the cycle again. A UROT on that second qubit, this time starting from 2 and going all the way to, because there's one less qubit to deal with here, you have UROT going up to n minus 1. And that comes down here. And so on. So this construction is exactly what gives you the quantum Fourier transform. So remember, I've only shown you the gates for the first 2 qubits. Of course, this has to happen for all of the qubits as well. Now, we could go into an explanation of why this works. I'd like to, instead of showing you how this works for the entire circuit, just focus on just the first qubit. Let's talk about these gates that I'm going to put stars on. We'll talk about these gates. So what's happening? Let's start here, and I'll write down all of the state after each of these points. So I'll call this step 0. And I'll call this so step 1, 2, 3, 4, and so on, going up to step n. What happened at step 0? So let's assume all the qubits started in the 0 state. Step 0, well, actually, I take it back. The qubits don't start in the 0 state. They start in the generic states x1, x2, x3, all the way up to xn. Otherwise, there wouldn't be a point to all of this. Step 0, the state that we have is this. Nothing surprising here. Step 1, we're going to have the following. So all we've done is apply one of these UROTs, and it's being applied on x1. So I'm going to separate out x1 from the pack. So it's going to be 0 plus e to the 2 pi I. Remember the action of a UROT. It's e to the 2 pi I over 2 x1. And then all the other qubits. Okay, that's the action of that first U rotation. Step 2, maybe I'll scroll up and keep that in view. Step 2 does exactly the same thing for x2 with a different phase. So you get 0 plus e to the 2 pi I over 2 to the power of 2 x2. And then you also get e to the 2 pi I over 2 to the power of 1 x1 on 1. Times all of the others. Excuse me. Okay, step 3, let's write down. We do exactly the same thing with x3. So e to the 2 pi I over 2 to the power of 3 x3, e to the 2 pi I over 2 to the power of 2 x2, e to the 2 pi I over 2 to the power of 1 x1, 1, with all the others. Eventually, you'll get to step n, which is 0 plus e to the 2 pi I over 2 to the power of n xn, e to the 2 pi I over 2 to the power of n minus 1 xn minus 1, going all the way through e to the 2 pi I over 2 to the power of 1 x1 on 1, and then all the other qubits. All right, I hope you can see this now coming into view, right? So this exact thing that I wrote down, let's ignore all the other qubits because we haven't talked about what the gates on them do. This expression right here is exactly equal to what I wrote at the very top here when we were talking about things. It's exactly equal to e to the 2 pi I, this term right here, x over 2 to the power of n. So it's exactly because of this issue that we have the ability now to say, notice this was the last qubit, right? So this is the very last qubit. Here, x1 is the very first qubit. So there's a reverse order in the way this circuit works. But if you look at it carefully, it exactly implements what we did with the QFT. So this circuit implements QFT, except in reverse order of the qubits at the output. And in fact, this is something that's not just really cool to see, but what I'd like to do is also convince you that you also can go write a function that does exactly this and build out a quantum Fourier transform. So Brian, I'm going to start sharing my screen very quickly in order to show exactly how this works. So if you remember earlier, I showed you a demo. And in this demo, I used Qiskit's built-in quantum Fourier transform from its circuit library. In fact, I can do exactly the same thing in a demo, a notebook that I'll show you after lecture. What I'm doing here is building out quantum Fourier transform myself. So I'm saying my quantum Fourier transform, and it's a very simple function. I'm creating the circuit, and then I'm saying for each of these qubits, apply a Hadamard, and then do a series of rotations where the phase is exactly as we've discussed.
If you don't mind, could you just please zoom in on the code a little bit so it's more clear for people at lower resolution? Perfect, thank you.
I think this will do. So this is exactly what we wrote down in our derivation. I'm applying a Hadamard, and then I'm applying a series of U1 operations, which is exactly the kind of gate that we talked about in the derivation, what we call the UROT. And this is the phase that I'm applying. And I'm doing a loop, so I'm doing all of these phases. And I'm doing it for all of the qubits. So in the end, for a 4 qubit, when I call this function, I apply a Hadamard, I apply the phases for it, and then I apply a Hadamard, and then I apply all the phases for that qubit. So this is my own custom-built QFT, which is exactly what I've done here. And this is QFT that Qiskit does. It's exactly the same thing with a swap at the end. And there's a swap at the end because Qiskit is trying to help you with that reversed ordering of the qubits that I mentioned in the output of QFT. So that's, I hope, a very clear demonstration to you that QFT is really building out in a very simple way. It looks like this. Now, to convince you that all of this works as you'd expect, I've done exactly the same thing where I show you the computational and Fourier basis using my QFT. So if you look in the code here, I'm doing my QFT instead of Qiskit's own QFT, and it produces exactly the same results. And in fact, for 3 qubits, I can show you exactly how this works with my QFT. This is the state 0. This is the state 1. This is the state 2, and so on. So I'll send you this demo notebook on Discord so that you can also see exactly how all of this works. But I hope this has convinced you that writing down the QFT at the end of the day boils down to writing this loop. It's applying a Hadamard and then a series of rotations and doing that for all the sets of qubits. Okay, I think we're on the top of the hour. I hope you're convinced that the implementation of the quantum Fourier transform circuit is, as we've seen here,